All right, let's get right into one of the most fundamental concepts in all of physics, how the universe communicates, from the light you see to the sound you hear.
And you know what? That code is written entirely in the language of waves. Today, we're going to crack it.
Okay, first things first. Before we can get into the really weird stuff, we have to understand the basics. What exactly is a wave? Think of amplitude as the wave's intensity. For a sound wave, a bigger amplitude just means it's louder. For light, it means it's brighter. It's really just how high the peaks are and how low the troughs are from that middle resting line.
This is literally the length of the wave. We use the Greek letter lambda. You see it there, lambda. It's simply the distance from the crest of one wave to the crest of the very next one. That's one full cycle.
So, frequency. That's how often the wave is oscillating. How many of those complete wavelengths pass by a single spot every second. And here's the crucial part. It has an inverse relationship with wavelength. If you have a super high frequency, with waves coming one after another really fast, then those waves have to be shorter, right? They have to be squished together.
And all of that comes together beautifully in this simple, elegant formula. V equals F times lambda. A wave speed V is just its frequency, F, multiplied by its wavelength, lambda. Honestly, this little equation is the key to understanding pretty much any wave you can think of.
Now, waves basically come in two flavors. You've got longitudinal waves, like sound. Imagine pushing a slinky. You see a compression travel down its length. The wobble is in the same direction the energy is moving. Then you have transverse waves, like light. Think of making a wave on a rope. You shake your hand up and down, but the wave itself moves away from you, at a right angle.
All right, so now that we've got the basics down, let's get into the really cool stuff. What happens when waves start interacting with each other and with the world? These are the rules of the game.
Here's something wild about waves. Two of them can be in the exact same spot at the exact same time. They don't bounce off each other like billiard balls. Instead, they just add up. Their individual heights combine to create a brand new temporary wave. This is what we call constructive interference. Imagine two waves, and their peaks line up perfectly. They're in phase. What happens? They join forces. The peaks add together, and for just a moment, you get one big superwave with a much larger amplitude. And, as you might guess, the opposite can happen too. This is destructive interference. What if the peak of one wave meets the trough, the lowest point of another? Well, they're out of phase. In that case, they cancel each other out. If they're perfectly matched, poof, the wave can just disappear entirely for that instant.
Diffraction is another one of those classic wave giveaways. It's just the tendency for waves to spread out as they pass through an opening or bend around an object. It's the whole reason you can hear someone calling your name from another room. You don't need a direct line of sight because those sound waves literally bend around the doorframe to reach your ears.
And when waves pass from one material into another, say from air into water, they bend. This is called refraction, and it's all described by Snell's law. N1 sine theta 1 equals N2 sine theta 2. That equation tells you exactly how much the wave is going to bend. The classic example? A straw in a glass of water. It looks broken, right? That's refraction in action. It's the light from the straw bending as it leaves the water and enters the air on its way to your eye.
So for a really long time, this wave model seemed perfect. Light is a wave. It diffracts, it refracts, it interferes. Case closed. Right? Well, not quite. There was this one little experiment, this one annoying result that just didn't fit, and it was about to change everything.
So what happens when your perfect theory can't explain what you see with your own eyes? That's exactly the problem scientists faced with a phenomenon called the photoelectric effect.
Okay, so the experiment was simple enough. You shine light on a piece of metal, and sometimes it spits out electrons. But the results made no sense for a wave. First, if your light's frequency was too low, nothing happened. It didn't matter how bright you made it. But wave theory said a brighter wave has more energy, so it should have worked. Second, there was no time delay. The electrons popped out instantly. A wave should take time to pour its energy into an electron. It was all wrong.
The solution was so radical it turned physics upside down. Einstein came along and said, what if light isn't a continuous wave at all? What if it's actually made of tiny individual packets of energy, little bullets of light? He called them photons.
And this idea came with a new equation, E equals hf. The energy, E, of one of these photons has nothing to do with brightness. It's directly proportional to its frequency, f. that h is just a number, a fundamental constant of the universe called Planck's constant. This was huge. It meant that blue light, which has a higher frequency, is made of more energetic photons than red light.
And suddenly, everything made sense. It's a one-on-one deal. An electron gets hit by one single photon and absorbs all its energy, instantly. That's why there's no time delay. If that one photon has enough energy to overcome the metal's work function, the energy holding the electron in place, then out it comes. If not, nothing happens. It perfectly explained everything. But this was just the beginning. This idea that light could be both a wave and a particle wasn't just some weird quirk. It turned out to be a fundamental secret of the entire universe. This is where a physicist named Louis de Broglie comes in with this absolutely mind-bending idea. He thought, okay, if waves can act like particles, maybe particles can act like waves? I mean, why not? Maybe all particles, electrons, protons, you, me, everything has a wave nature.
And he even wrote down the equation for it. Lambda equals h divided by p. The wavelength of any particle, lambda, is just Planck's constant, h, divided by its momentum, p. Think about that. It connects something that only particles have, momentum, with something that only waves have, wavelength. It's a bridge between two different worlds.
And you know what? He was absolutely right. This wasn't just a cool theory, it was proven in a lab. When you fire a beam of electrons through a thin crystal, they don't just act like tiny pellets and make a single dot on the other side. No way. They create an interference pattern, just like light waves do. It's undeniable proof. Electrons are also waves.
So, what is it? A particle or a wave? The bizarre, beautiful, quantum mechanical answer is it's both. Depending on how you look at it, it behaves like one or the other. This isn't just a puzzle, it's a fundamental feature of our reality. It shows that down at the very smallest scales, the universe is so much weirder and so much more wonderful than we could ever have imagined.